As a brief introduction of our speaker, we have with us Professor Dr. Reinhard Genzel, Nobel Laureate in Physics, Max Planck Institute for Extraterrestrial Physics, Garching, Germany. Uh, a special lecture on galaxies and black holes, a 40-year journey. So, without any further delay, I request our speaker to start the talk.
Okay, well, thank you very much for the invitation to you all. And my story is one of science, yet you will see that, of course, the motivation to do this kind of work, of course, drives from spirituality in the sense of being curious. And I'll explain that in a sort of a parabola in a second. So the question, of course, in the end is whether objects which were predicted more than 100 years ago by Albert Einstein and his theory of general relativity, whether they're really there. And that, of course, is what we as experimental natural scientists are supposed to do, right? We hear ideas, proposals, and we are curious to understand whether these proposals are correct. Now, of course, there is always the question of whether this quest between for scientific understanding and curiosity and spirituality and religion are in contrast, or whether they can merge. For me, this is a personal question. My mentor, who has been with you a long time ago, Charles Towns, was very religious, and there was no discrepancy between his spirituality and being a human being and the goodness he had and his scientific curiosity. I've grown up as a not religious, but certainly not very religious person. And for me, the question of spirituality, as you will see, is more like that of exploring a forest. The forest is a picture of the universe. There you see, there's a forest. And it's clear that the spirituality, the nature of this wonderful forest speaks to all of us. All of us humans, we see this and it's wonderful. See all the different trees, you see the plants. And as human beings, we are curious. We would like to understand what's there. So we go ahead and walk through this forest and discover next to the different types of trees and so forth, also flowers and mushrooms and many other things. So that's when we become explorers. Very typically, of course, human beings then have tried to find explanations. Why are these flowers there and so forth. Now, the experimentalists then start, say, looking at the flowers and see that there are red flowers and blue flowers. And then, oops, all of a sudden they find that the blue flowers are only on the left side of the path. Now, this is sort of an initial finding, but then when you do this carefully, then after a while, you have established an empirical truth. The blue flowers are on the left of this path. And the step toward the hard sciences then is to ask the question, why is that so? Why is that so? And so that's the story which I will tell you about one aspect of exploring our wonderful universe in which we are, where so many discoveries have been made over the last 100 years. And so I invite you to a trip initially out of our Milky Way into the nearby universe. All right, so what we've just done was to fly with what effectively actually is but 10 times the speed of light through our local village. Amazingly, that local village which we have visited here, the real pictures of galaxies, the island universes, so to speak, one of which is our own. The light takes 50 million years to cross what we have just done. 50 million years. Yet that village is just a small part of the universe, which, for all we know at this point, is infinitely large. That's remarkable. We don't understand all the aspects, but we are learning. Now, of course, a key element of all of this, we already knew back during the times of the Greeks and the Babylonians, that's gravity, the force of gravity, which attracts masses. And of course, for humanity, the best example everyone knows are the planets and the sun. The sun, which dominates the mass, and the planets which orbit that sun on, almost circular orbits at different radii. The inner ones, like Mercury there or Venus, faster, and the outer ones, Saturn, Uranus, and Neptune, they're slower. That is what we mathematically know as the Kepler laws. And that is a characteristic of the fact that the sun dominates the gravitational environment around it, and the planets are forced to move on these orbits. And so this is something, of course, which observational astronomers, got more and more information on over the period since 1600. See all the famous people there, Galileo, Copernicus, Kepler, Newton, and also Tycho Brahe were people who really, with ever greater detail, understood the planetary orbits and so forth. It became also clear that an earlier alternative, namely that the Earth was in the center while everything else orbits around the Earth, could not be maintained. It's just not consistent with the information. Now, this picture of the gravitation and the solar system, I should say, does not depend on the shining of the sun. So if you would switch off yeah, the light, so to speak, of the sun. Otherwise, everything being equal, the planets will still go around more or less in the same fashion as they do with our sun being on. So this picture of gravity being a force which is attractive and keeps things together, solar systems, but also galaxies is of course, which is sort of the basic truth of our forest, which we are finding. But then the next big step forward was general relativity. Now, general relativity followed from the work of Einstein in 1905, which we call special relativity, where he basically took into account two experimentally very strong facts. Number one is that nothing can be communicated at faster than the speed of light. Nothing. Speed of light is, so to speak, the speed limit of information exchange and as we also now know experimentally, of the communication of gravity. So it's not like Newton, who thought that if you put a mass magically into the center of somewhere, and immediately the force of gravity from that sun is felt everywhere. No, it takes the speed of light to distort the what we call the space-time, and so then this mass is felt by other masses. Now, the equations of general relativity have another feature which comes from Einstein's earlier work, and that's the equivalent of mass and energy. You may have heard the equation energy equals mass times speed of light squared, E equals mc squared. So that means, although what we now call photons, light, have no mass, they have the equivalent of mass, and therefore they see gravity. So with these two facts and a new way of mathematically formulating the gravitational theory in more general terms, Einstein in 1915 published or spoke for the first time about this new theory. The next year, Carl Schwarzschild there found the first solution, and that solution already in a spherically symmetric spacetime it contained the picture of a black hole. Then it took quite a long time, about 50 years, for the mathematical foundation of that theory to get ever firmer. Other solutions were found, like Roy Kerr, for instance. Roger Penrose was able to generalize the the solutions to a non um, symmetric part. Just the curvature of space-time is the key thing. And then, of course, came the question: what happens to on small scales, and what happens to entropy? What happens to information exchange? Which is what we still don't fully understand, but is at the very center of much activity currently. Now let's think of our sun again. There we go. And if you Newton and you let a rocket take off from the sun, then in order for that rocket to escape to infinity, it has to have a minimum speed of about 600 kilometers per second. That minimum speed depends on the gravity of the sun, and the gravity of the sun depends on the mass of the sun, but also on the radius. It's the ratio, not just the mass. So on Earth, which is both less massive by far and also smaller, that escape speed is 11 kilometers per second. And since the 1960s and 70s, we know that practically by being able to fly spacecraft into the environment and now even to very large distances from the Earth understanding this theory. Okay, so I said that the gravity of the sun there depends on the mass and the radius. Now suppose we leave the mass as constant, but now in our Duncan experiment make it smaller, then gravity increases. So suppose we push it all the way to 3 kilometers, so much smaller than it is now. Then we can calculate again how fast the rocket would have to fly, and it comes out an astonishing speed of 300,000 kilometers per second, because the gravity is stronger from a smaller from a mass concentration which is smaller than the one we had before. 300,000 kilometers per second. That's the speed of light. If you make it a millimeter smaller, then it's greater than the speed of light, and that's not possible. So now you basically understand that the theory says there must be a situation, or there can be a situation, where the mass is so strong that from within this region called the event horizon, which is proportional to the mass, no light can escape. But not only no light, also no particles. But then, how can we see what we cannot see? How do we possibly can know that such objects we call black holes exist? Well, through their gravity. So if you think there is this object with one solar mass, and you would have the same planets orbiting it, well, they would more or less move with the same speed. So you can then use the motions of the planets to conclude that there is an object in the center which we cannot see, but which has one solar mass. So that's one of the tools how we can nowadays look for black holes. Now, the first astronomical objects where black holes came into play were the so-called quasars. In the 1960s, the radio astronomers started using their new radio telescopes to chart the skies, and they found, very bright radio sources, variable sources with in large numbers. And so then when you look at the sky at that position in the optical, what you see is, like in this case, a source discovered in Cambridge, England, a mega little star-like object. And so nothing very special, yet the radio source is very prominent. Then Martin Schmidt down there at Caltech, using the biggest telescope at that time, the Palomar 5-meter telescope, took what we call a spectrum. That is, you split the light in a different wavelength. And when he did so, he saw that there were very prominent emission lines in the optical spectrum of this object. And their wavelengths, however, were all redshifted by 16% compared to the laboratory. 16%. How could that be? Well, okay, already in the 1920s, Hubble had, of course, found that the universe is expanding. And in an expanding universe, the expansion speed appears to be larger if the object is further away from you. So if you take that 16% and convert it, knowing the expansion of the universe into a distance, then this object here must be 2.4 billion light years away. That's enormous. At the time, there was if you like, a world record. The universe at that time was what I showed you in the movie before, the nearby universe of galaxies. 2.4 billion light years. Now we know, of course, that there was a Big Bang, which is sort of the beginning, if you like, of our current universe, and then the universe expanded thereafter. This is a significant fraction of that time since the Big Bang. So this object is extremely far away. So are other quasars. Well, if they are so far away, then although they don't look very bright, they have produced a lot of energy. So if you go into the reference frame of that object there, the luminosity which comes from that little star is the equivalent of 1,000 times that of the Milky Way with its 100 billion stars. Wow, how could that be? So the theorists in the 60s started thinking about various options. It was a long, long wrestling about what the solution might be. And what came out in the end was, something completely paradoxically, black holes. The picture which developed was that at the center of 3C273 sits a black hole, but not of one solar mass, but in this case of several billion solar masses. So now, if you have such a big black hole, well, of course, you cannot see it, as we discussed, but it, of course, attracts gas and stars and everything else from the vicinity, and that material will spiral inwards if it has some angular momentum or fall directly in if it doesn't. And before it actually disappears behind the event horizon and is then not visible anymore, it can convert the gravitational energy in radiation. And if you take the equivalence of energy and mass, then the efficiency of converting mass into radiation close to the event horizon can be as large as a few tenths of percent. Wow, that's 1,000 times more productive, so to speak, more efficient than the fusion of hydrogen into helium in stars. So that's why was the idea quasars can be so bright. But that is, of course, very rare, apparently, because the number of quasars which were found in the next 10 years after the first discovery was several tens. Nowadays, we know many, many thousands or even millions, but they are far away typically, very far away. And Lyndon, Bell, and Rees, two of the theorists working on that, with whom you see down there, proposed the reason for that was for this distance is that if you have a black hole, very rarely do you accrete as much material as you would in a quasar. But, and that was the other side of their proposal, it could be that black holes as such are much more common than in these quasars only. And maybe, so they wrote in 71, such black holes could also be present in some, if not all, nearby galaxies, including our own. So that is when the hunt for the testing that theory really started in the late 60s, early 70s. Charles Towns then had just moved to California. He got his Nobel Prize for the invention of the laser, but then he started, looking into infrared radiation and infrared astronomy. So he and his group, and I joined that group as a postdoc, found the following thing. In the center of our Milky Way is a very dense star cluster, a million times denser than the solar environment. These are these blue objects. Then there is in the center of that a very compact radio source. We now know it's only several tens of micro arc seconds in size. 10 micro arc seconds at the distance of the moon would be about 5 to 10 centimeters. So very compact radio source. And then there's gas, which is, as you see, either ionized in pink or neutral in green. And Towns and his group then charted the Doppler motions of this gas around the black hole and use the technique which I described to you. Check out how fast the gas moves at different distances. And if it moves faster in the inside near Sagittarius A star and slower outside, just like in the solar system, you can conclude something about the mass of Sagittarius A star. And that's depicted on the right side there from a paper in the 1980s, where we basically had shown that the enclosed mass on the vertical axis increases from the center outward, but as you go below about a distance of a few light years from the center, the mass stays more or less constant. And that is what you would have if you have a point mass, and much denser than what you would expect to see with a star cluster. So Towns and our group in Berkeley were pretty convinced at that time already that that means that there might be a million solar mass, few million solar mass black hole coincident with that radio source, Sagittarius A star. But nobody else believed this. That is science. Just because somebody says it doesn't mean that everyone else has to believe it. You have to actually provide proof, and others have to also check this out. And so it took from then on 40 years to where we are now, and that I will sketch out for you. Now, for of our galaxy are actually extremely compact objects. Therefore, the chore to make these measurements of moving objects, gas, and as you will see, in particular stars, requires very big telescopes, which came into operation in the 1970s, 80s, and 90s. Here you see the VLT, which is currently the biggest such facility. There was four such telescopes, which you can even combine to a single machine of 130 meters in equivalent diameter. And so big telescopes, and you need to have good in sensors. In the galactic center, you can't do that in the optical. You have to go to infrared waves or radio waves. And then, of course, there is the Earth atmosphere, which disturbs the images. And to overcome that, we basically analyze light from the distant objects and correct for that disturbance. And that's called adaptive optics. So all these technologies took many, many years, and that's why the progress was in phases, fantastic phases, always forward, but it took time. Generations of young people have been working with me and others to go where we are now. Now we can go into the center of the Milky Way in a virtual trip. That black stuff are dust clouds, but you see the many stars. But the center you cannot see in the optical, they're hidden behind dust. But then you can go to the infrared, that's what we're doing now. And there it is, the central star cluster. And with the big telescopes, you can really resolve that. And then, if you have patience, you can take pictures initially every year, in the end, every day. And you see the stars move very fast, much faster than in the solar system. So that's already the first indication that there is a central mass. And with the interferometric combination of the telescopes, we can now see that motion around Sagittarius star within a year. This is on scales of Neptune's orbit. You see down there the blue circle indicating that some of the stars, when they are near Sagittarius star, move at 8,000 kilometers per second. So that's a significant fraction of the speed of light. And so from that, we can learn, that there is a very compact object. You can learn how much mass the object really has, etc. So this is detailed, painstaking work, which cannot be done in one go. And in this particular case, also had the benefit of two groups independently going that route. That of my group with, as you see, some of my leaders, Frank Eisenhower and Stefan Gillissen, and then my colleague Andrea Guess and Tuando and others at the Caltech institution with the Keck telescopes. And so, the two groups found essentially the same motion for this one star there. You see, there is a star which moves on obviously a highly elliptical orbit. As the Sagittarius star is that dot, that black dot in the lower part of the image. So clearly this highly elliptical. And when it approached that star for the first time, Sagittarius star, it was only 15 light hours away. So that's about 3 times Neptune's orbital radius. And then it moved with 8,000 kilometers per second. So in terms of Kepler's laws, that's exactly what you would expect if there's a 4 million solar mass object. But must it be a black hole? And can we assume that general relativity is actually correct? So this was in 2002. And so then we said, well, we have to obviously wait until the star comes back. Being on an elliptical orbit, it'll come back. And we measured that period to be 16 years. So we knew that the star would come back in 2018. And down below, you see with our new interferometric resolution, 20 times better, we could then see the motion of the star from night to night at 8,000 kilometers per second. And the star at a distance, as I said, of Neptune's, a few times Neptune's orbit, which is the equivalent of 1,400 times the event horizon. of a black hole with 4 million solar masses. So that's very strong evidence, but it's not incontrovertible. Many people have suggested alternatives because it's still, sort of within 1400 times the event horizon, many things can happen. We know the mass of that central object to a fraction of a percent. Likewise, we can measure the distance to the galactic center with unprecedented quality. That's very important for what is to come. And for what is to come and has been done now is to test general relativity for the first time near a black hole. For instance, if you have a star moving around a black hole, then as the star emits the light, it gets redshifted. The gravitational redshift in the case of the S2 star is about few by 10 minus 4. So that's the equivalent in velocity of a few hundred kilometers per second. And down below, you see if Newton would be right, there would be no such gravitational redshift. That's the gray constant line. General relativity prediction is the red line, and the data which we collected, you can see clearly follow general relativity. The next proposal, or not proposal, next effect you would expect is the so-called Schwarzschild precession. We talked already about the sun and the orbit of a star. In Newton, that orbit is constant in space, but not so in general relativity. In general relativity, the orbit precesses. It precesses in its orbit, like this, but it also can precess if the black hole has a spin. In any case, if you do the same thing as in the left diagram now in X and Y residuals, then the Newton answer would be there are no residuals, right? Because I mean the location, the orientation of the orbit is always the same. But general relativity, the red line, it predicts these loops due to the precession, and the blue are the data. So clearly, again, general relativity, explains the motions at 1,000 times the event horizon size. But of course, we would like to get much closer to the event horizon. Can we? Yes, we can, with two techniques. One is there's gas, very hot gas, which falls into the galactic center every few days. I mean, it does so in its last hours. It starts rotating around the galactic center at a few times the event horizon size with 30% the speed of light. So that's amazing, and we've been able to measure that motion. And again, it is consistent with 4 million solar masses. And then the next one, and perhaps the most exciting one of those techniques, is to use the photons themselves, radio waves, and use the technique of intercontinental interferometry. So there you see the Earth, the northern half, you see the telescopes in Europe, the United States, and also in Chile. And these telescopes were used at a few millimeters wavelength by the so-called Event Horizon Telescope Consortium to check out how the light is, moving around the black hole. Imagine there's such a black hole, and you look from the left there. Suppose next there is a source of light, this little blue dot behind it. Then, of course, the classical explanation would be that the light would not, of course, penetrate through the black hole, but immediately outside the black hole would come straight at us. In the case of general relativity, the explanation is a little more complicated. Even outside the event horizon, the light is enough bent so that it doesn't reach us. Only around about 2.2 times the event horizon radius does it come to us. And we know what the mass is, so you can calculate what that ring should be, that shadow, and it's 50 microarc seconds. And see, that's what our radio colleagues have measured. So that's another piece of evidence that within, a few times the event horizon size, the same mass we have measured with the stars so precisely is still there. So 40 years after beginning this experiments, the situation is as follows. We started plotting the mass, the enclosed mass in logarithmic units, vertically versus the radius, come from the outside. And, within, as I mentioned, within a few light years, you begin to see a more or less constant mass. And then using the stars as our best probes, we can move inward until we see these spectacular elliptical orbits like the star S2, which we discussed at 1,000 times the event horizon. And it's always the same mass. And then finally, we can use both the shadow and then the motions of the hot gas to see that the same mass is also at a few times the event horizon size. So there is not much additional material possible between the event horizon and where we have our innermost measurements. We can sort of set a limit. So there's a little bit of something due to the error bars of the measurements, of course, but this looks like a black hole. Of course, we would like to still go closer, still measure more precisely, and I'll come back to that in a second. So we now have seen that in the case of the galactic center, indeed, as predicted by Einstein, Schwarzschild, and all the others, there can be a mass concentration which looks like a black hole, in this case of moderate mass, but that can, of course, be different in different galaxies. Let me finish with a few comments about the future. Are we done? No, we are not done because we have not yet, as I said, we have not yet been able to go, right at the event horizon, exclude that there is, after all, either a change in the theoretical or interpretation, or there is another configuration. Currently, we have a wonderful telescope developed by NASA in orbit, 2 million kilometers away from the Earth, where it's not disturbed. And that telescope discovers very distant quasars and very distant galaxies, and therefore objects which were formed very, very long time ago, close to the Big Bang. In 3 years, you will have a telescope in Chile next to the VLT, which will have 39 meters in diameter. Remember, the VLT telescopes and the Quack Keck and so forth have diameters of 8 to 10 meters. So this is still a bigger and better resolution. And we hope to use these telescopes to look into the distant universe. Then NASA and ESA are planning an extremely ambitious mission to detect gravitational waves in interstellar space from such black holes, maybe in 10, 15 years from now. So if that were possible, and I have every confidence that it will, then we can do the following experiment. If there's a stellar black hole, a little one spiraling into a big black hole, then in this case, this is the potential curvature of space-time. You see the little object and then the big black hole. Then this will spiral inwards. And this motion, if the theory of general relativity is correct, can be fully explained with two numbers, the mass and the spin of the black hole. Everything else is a function of these two quantities. I mean, this is very different from the Earth. If you want to describe the Earth from the outside, you have to have many multiples of the gravitational moment because of the mountains and the seas, the oceans, the valleys, and so forth. Not on a black hole. The theory of general relativity predicts a black hole to be a superbly simple object, very simple. Now, how did it get all started? We are now in this diagram of activity versus time on the right side. We see, very few stars being formed in galaxies like our own, and very few quasars. But if you go back 10 billion years, that changes by a large factor. And we are charting out now, and have been doing so, the evolution of star formation in galaxies, the growth of galaxies, and the growth of black holes, as indicated by the quasar density. And what we see, that there is a peak, and the two track each other. So they grow together. That is because there is material falling into the galaxies, which then some of it makes it into the center, and that makes the black hole grow. But of course, how close does that go? And the James Webb Telescope has now seen objects which is less than 1 giga-year after the Big Bang. So that's something we don't quite understand how that could be. Is it that there are growth processes which are faster and different from what we thought they were, or are there black holes perhaps even formed during the Big Bang? All of these interesting questions remain. Another even bigger question, of course, is what's inside black holes, and you might ask that in a sort of a, being curious. Can we fly into a black hole? Sure. If we are stable enough, we can take a rocket and fly into the event horizon, but we can't escape. We can't send out messages to our friends back home. In the end, we all will fall into what's in the center, a point of infinite density as predicted by general relativity. But is that correct? If we would have a theory which is also describes the quantum nature, we don't know. So there are many, many questions about black holes. Black holes are sort of the most fantastic objects. We now know that they do exist. We are beginning to learn how they have been forming, but there are many more questions left over. Thank you very much.
Thank you so much, Professor. Thank you for such an elaborate discussion, such a lively discussion, which cheered our audience. So now, with your permission, we may proceed to the question and answer session.
Sure, of course.
The first question: is there a theoretical limit to how far can we look into universe?
Well, I mean, at this point, it's again the speed of light and the current age of the universe. And of course, we have information coming to us from a time just after the Big Bang. I mean, a few 100,000 years after the Big Bang. And there's a relic radiation, the cosmic microwave background radiation, which we can study nowadays in great detail. And that we can use to ask the question whether, is there a finite size of the universe? And so far, the empirical evidence is no. But we will keep looking because that's what scientists have to do.
Thank you. The next question, you mentioned about speed of light as highest. What about experiments of non-locality in quantum mechanics and John Bell's works, which hints communication beyond speed of light?
Yeah, that's a classic issue, of course, and the answer is it looks like communication, but it's not communication in the sense you would like. So what you can do, and Nobel Prizes have been given for that, is to prepare, say, two particles in the quantum state, which is correlated, and then you let these two particles fly apart, and then a while later, when they are at a very large distance, you measure the quantum state of one particle, then you can predict what the other particle is like. But that's not communication. That's only because you have prepared the system to be in a coherent state and so forth. So no, there is no evidence for communication in this normal sense of the word.
Thank you, Professor. The next question, the Nobel Prize is awarded to the development in science that is most beneficial to humankind. How does study of black hole make it worth a Nobel Prize?
Well, okay, that's a hard one to answer. I think basically, uh, if you look at the first 60 years of the Nobel Prizes in physics, you will not find a single astronomer there. And that is because actually Alfred Nobel in his will had said in order to get a Nobel Prize in physics you have to, so to speak, do something which is useful. I'm saying this now in a very caricatured way. You cannot get it for just observing phenomena in the sky, for instance. You can also not get it for mathematics, right? And that has changed because astronomy has now become basically a physics laboratory, as I've shown to you. I mean, we are doing experiments in the sense of physics experiments, and from that we learn something about physics. We also learn something about the universe. I mean, that remains the same. Now, is it useful? Yeah, it's useful for curiosity. And again, my statement holds from the beginning. We are human because we are curious. We want to know. And that is in us from the time when we are little babies and little kids. Curiosity to understand how everything is together. And so in that sense, I would say one changes things. Now, of course, on the way, technology is being produced. Charlie Towns got his Nobel Prize for the laser and the maser, but he did not do the work which then led to the Nobel Prize because he wanted to get the prize for the laser and the maser. The laser and the maser were meant to be a lamp to look at molecules. Okay, so that's with many of the developments which are useful in the classical sense as technologies. They are byproducts of curiosity.
Thank you, Professor. One last question. How do asteroids happen to fall on Earth, and where do those asteroids come from? What is the reason behind of falling of asteroids on Earth?
Well, it's not only asteroids. Remember, there's also other celestial bodies like comets and so forth, which can come very close to the Earth. And the reason is that in the formation of the solar system, the basic picture is you form, a extended system of gas initially, then the central concentration collapses to a star, that's the sun. But then there's all the other stuff out there, and that also collapses, and that's the planets. And then you get planets of large sizes, of small sizes, and not all planets are in circular orbits. Some of them are in, some of these, remnants of the formation of the sun also are in highly elliptical or even parabolic orbits. And so they can come in, and they have initially much more than now. I mean, that's why initially the Earth was bombarded. That's how the moon got formed, of course, by a collision with a heavy object. So we are now in the late stages of the solar system where these things are very rare, but in the early stages, that happened very frequently.